Okay, so this is the Laplacian in polar coordinates. This is the Laplacian, sorry, this is the Laplacian in Cartesian coordinates. This is the Laplacian in polar coordinates. I'm using the similar symbol, except here I'm writing r theta, just to let us know, hey, this is the polar coordinate representation. Okay, so what this suggests is the following. If u satisfies, if u of xy is a function that satisfies the Laplacian of u is equal to 0, well, if I look at the polar coordinate version of the Laplacian, I kind of have these two separate terms. I have some terms involving r and some terms involving theta. So the first two terms only involve r derivative. The third term involves the theta derivative. So let's think about this. If I have a function of two variables that's really only a function of the r variable, that is in the formula for u, wherever I see the variables, they just show up as like x squared plus y squared, something like that. Then when I take the derivative, the theta derivatives are going to be equal to 0 because it doesn't depend on theta. The solution doesn't depend on theta, it just depends on r. And so what that's going to do is to give me an ordinary differential equation that I can solve. So let's say I have a function u of xy that solves the Laplace's equation. And let's assume furthermore that it has this special form, u of xy. In Cartesian coordinates, we would say this is a function of the square root of x squared plus y squared, but in polar coordinates this would just be v of r. Okay, so in other words, what I'm saying is assume we have a function of this form. U of xy is a function of x squared plus y squared, or in polar coordinates just a function of r. So we can always find functions like that, but I'm also assuming that it solves Laplace's equation. And now, if such a function exists, I want to find out what that is. So if such a function exists, I want to find out what that function is. Okay, so if I'm dealing with polar coordinates, so I've switched to polar coordinates here. So if I want to compute the Laplacian, I'm going to use a polar coordinate version of the Laplacian. So I'm going to have 0 is equal to 1 over r times the derivative of r with respect to theta. So that's going to be 1 over r. Sorry, I said the derivative of r with respect to theta. That was just, I don't know what happened. I meant to say the derivative of v with respect to r. V prime of r, and then plus just the second derivative, v double prime of r. Okay, notice what's happened here. The double theta derivative is equal to 0 because v is only a function of r. Okay, so this term is equal to 0. Now, what this tells us, again, so the point here is that I can just think about v as being a function of r, and now I have an ordinary differential equation to solve, and it's much more comfortable to solve ordinary differential equations. So if I look at this equation here, I encourage you to think a little bit about how we might solve this. Okay, it's a second order equation with non-constant coefficients. So we know how to solve second order equations with constant coefficients, and we know how to solve first order equations with non-constant coefficients. So we need to either somehow convert this to a second order equation with constant coefficients, or see this as a first order equation with non-constant coefficients. You might remember from your differential equations class, you did something called reduction of order. Reduction of order was, among other things, was one way to convert a second order equation with non-constant coefficients to one that you can solve. So you might think about that, but if you look back through the method, you get something very similar to this. So what we need to do then is think about this as a first order equation, not for the variable or the unknown function v, but for v prime. So I'm going to view this as a differential equation for v prime, and then from that, once I know what v prime is, I can figure out what v is. So if we rearrange things, this tells us we've got v double prime over v prime. Actually, I need some more room, so I'm going to scoot this over. We've got v double prime over v prime is equal to minus 1 over r. Now, v double prime over v prime, this is the derivative of the natural log of v prime. By the way, whenever I write log, I mean the natural log. Okay, this is just by the chain rule. It's 1 over, if you do the derivative here, it's going to be 1 over v prime times the derivative of v prime, which is v double prime. Okay, so if we anti-differentiate both sides, we're going to get log of v prime on the left-hand side is equal to minus log r, and we typically think about r as being a positive variable, so we're not going to do absolute values here, but you can if you want, plus some unknown constant, which I'm going to call a. A is going to get redefined as we go along. Okay, so I want v prime, that's sort of my penultimate goal now, so I want to find v prime, so I'm going to raise e to the power of both sides. On the left-hand side, I've got v prime of r, and on the right-hand side, this is going to be equal to e to the a times 1 over r. Okay, but since e to the a is just another generic constant, instead of writing it e to the a, I'm just going to write it a. So this is equal to a over r. Okay, so these are like different a's. This a here is e to the a there, but they're just arbitrary constants, and it's better to just write it like this instead of e to the a. Okay, so v prime of r is equal to a over r. Okay, well, I don't care about v prime of r so much. I care about v of r. So if I anti-differentiate v of r, or sorry, if I anti-differentiate this, and I realize this is sort of a great injustice to you. V prime of r, in order to make my v primes look less like u's and more like v's, they end up looking more like my r's. So this is v prime of r is equal to a over r. So now I want v of r. So v of r is going to be the antiderivative over here. So this is going to be a log r plus another arbitrary constant b. Okay, so now if we think back to polar coordinates, or if we think back that r, what r means in polar coordinates, what this tells us is u of xy. If u of xy has the form a log of x squared plus y squared to the 1/2, because r is equal to x squared plus y squared to the 1/2, plus b, this is going to solve Laplace's equation, at least on a domain that doesn't include 0, 0, 0. Because if x and y are both 0, this is not defined. So now what we're going to do is, just to make things look a little nicer before we move on to the next step, this is a little logarithm, so the 1/2 can come down. So again, I'm going to redefine a. The new a here is going to be equal to the old a over 1/2. This is times log of x squared plus y squared plus b. Now what we are going to do, we are going to say, we're going to make a new function called capital phi. This is going to be very important. It's called the fundamental solution to Laplace's equation. We're going to pick a particular value of a and a particular value of b. The value of b that we're going to pick is 0. That kind of seems obvious. That seems like just something that would be nice. And the value of a we're going to pick is much less obvious, but it's going to be minus 1 over 4 pi, and then log of x squared plus y squared. Minus 1 over 4 pi times log of x squared plus y squared. Okay, and this is phi is called the fundamental solution to Laplace's equation, which is minus Laplace u is equal to 0. Okay. Now here's what we're going to do with the fundamental solution to Laplace's equation. So if I do a finite sum of these guys right here, so let me write what I mean here. So let me just remind you, let me restate what phi is. Phi of xy is equal to minus 1 over 4 pi log of x squared plus y squared. Okay. So like I said, this is called Laplace's, the fundamental solution to Laplace's equation. Hold on one second, my computer has... This is called the fundamental solution to Laplace's equation. And if we look at sums like this, if I look at something like, A1 times phi of x minus some point, let's say, C1 y minus some point D1. So C1 and D1 are just two generic numbers or whatever. A2 phi of x minus C2 y minus D2. Okay, these are going to be solutions to Laplace's equation, aside of course from where there's a zero in either one of them where it's not defined. And so what we might think is that by adding these together, we're going to get more and more complicated solutions to Laplace's equation. And the answer is yes. And if we add infinite number, like a continuous sum of them, it becomes an integral. And we're going to get something that is close to Laplace, a solution to Laplace's equation, but it's not going to be quite a solution to Laplace's equation. It's going to be a solution to something called Poisson's equation. And this is important for us. I'm actually kind of explaining this maybe or going in a different direction than you might be used to here. So Poisson's equation is minus Laplacian of u is equal to some known function f. Equations like this arrive in situations where you have some sort of force distribution, like a charge distribution, or like a charge density, or a density of some sort of force, and then U is the potential, and then U will tell you like the potential energy at any point of that field. Okay, and you might have seen before that if you have point charges in the plane, like if we're not dealing with 3 dimensions, if you just have point charges in the plane, then the potential energy, the potential of that field is going to be a sum of these logarithmic functions. And it's because it's going to we're going to end up seeing these as the solutions to Poisson's equation. Okay, so my claim is the following. My claim is the following. My claim is that the Laplacian of phi is equal to the Dirac delta mass in the following sense. If we define u of xy, if we define u of xy to be equal, to the double integral over the whole plane, so over R2, I'll say here. If we define u of xy to be the integral over R2 of, so now I have my variables here, x and y on the outside. My variables of integration I'm going to call a and b. So I've got phi of a, b. These are going to be my variables of integration, times f of x minus a, this the other way, a minus x, b minus y. Okay, so if I look at this integration, minus Laplacian of u is going to be equal to f of xy. Okay, so in other words, if we want to think about doing things formally, another way that we can write this double integral here, this is the integral over R2. If I do a change of variables, I can write this as phi of a minus x, b minus y, f of a b dA. Again, if I just do things formally, I have minus Laplacian of u. Okay, what I'm going to do now is I'm going to put the derivative. I'm going to do the illegal move of moving this minus Laplacian inside the integral. And so we're going to get minus Laplacian phi of a minus x, b minus y, f of ab. Okay, so what this tells us then, what I mean by this, or what my claim is that this is equal to f of xy. Okay, now moving the Laplacian on the inside is not legal. So this is wrong. However, what I will show in the next video is that if you define u this way and take the Laplacian in the xy variable, you are going to get out f of xy. So therefore, if we kind of allow this formal moving of the Laplacian on the inside of the integral, well, what we're saying is that if we do this integral here, it just reproduces f of xy, but that's exactly what the Dirac delta function does. Okay, so this is one of those things where we're not technically allowed to move the Laplacian on the inside. But if we move the Laplacian on the inside with the understanding of the theorem that I'm going to show you in the next video, then everything is more or less okay. This is one of those instances where you remember back from when we were looking at Fourier transforms, we have the limit on the outside of the integral, like the limit of the sine functions on the outside of the integral, and we said that the limit of the sine functions, or the sine in x over x, those functions, the limit of those functions are the Dirac delta, are equal to the Dirac delta function, in the sense of keeping the limit on the outside of the integral, you get the same thing. Similar things can be said here. Okay, so in the next video, I'm going to prove that if you define u this way, then the minus Laplacian of u is going to be equal to f, where again, phi here is the fundamental solution, minus 1 over 4 pi times log. The minus 1 over 4 pi will become clear why we're choosing that instead of something else in the next video.